Good afternoon, guys. We are getting to the end of the course. We have about 2 weeks left. There's still a little bit of information I have to get out to you guys. So there's going to be this video and then one more video plus your lab classes. But in the last couple of videos, I would like to go through temperature conversions and talk about RTDs, thermocouples, and thermistors. I'm also going to post a YouTube video that I found that illustrates all those three components fairly well. So I would appreciate if you would watch that as well. It's not very long, it's only about 7 or 8 minutes, but it might give you a little bit better visual representation of what we are talking about. So first thing first, I want to talk about temperature conversions. Temperature conversions. And there are four different values that we are going to look at. We are going to look at Celsius, Fahrenheit, Kelvin, and Rankine. Celsius and Kelvin are on the same scales, and Fahrenheit and Rankine are on the same scales when you end up looking at them. Typically now we would obviously use degrees Celsius as the value that we would measure everything in Canada. The United States uses Fahrenheit, although if you went back 25, 30 years, Fahrenheit was the most prevalent value that was used, and we didn't really use Celsius all that much until we went over to the metric system. So you will see a lot of temperature sensing equipment that still has Fahrenheit. A lot of the older generation prefer using Fahrenheit, and then as we end up getting to people that are maybe in the 30s and 40s, they like to go and bounce between the two of them. Haven't really landed on one that they like more than the other. But let's go through these. So if we were to look at them on a scale, and I looked at 0 degrees Celsius, and if we looked at 0 degrees Fahrenheit, and we looked at the absolute coldest value we could get, the absolute coldest value you can get is absolute 0, and that is 0 degrees Kelvin. And 0 degrees Kelvin is negative 273.15 degrees Celsius. Sorry, I did make that a little small. So 273.15 degrees Celsius. So that would mean then 0 degrees Celsius is equal to 273.15. Actually, we'll get rid of this for now. Degrees Kelvin. Okay, and if we were to go up to the boiling point of water, which is 100 degrees Celsius, we would just add 100 degrees Kelvin onto this value because they go at the same rate or increase at the same rate. So we get a value of 373.15 degrees Kelvin. So fairly straightforward, and I'll lay out all the formulas a little later. Let me just move this camera down a little bit. So I'll go through the formulas in a little bit. So that was our little scale, and obviously all the values in between. So let's look at the other scale again. Draw it over a little further. So we have 0 degrees Fahrenheit, and we are going to have our absolute zero value. So absolute zero value in Rankine, so 0 degrees Rankine is equal to negative 459.67 degrees Fahrenheit. So I know a little tight in there. So negative 459.67 degrees Fahrenheit. And if we went up to 0 degrees Fahrenheit, obviously, that would be 459.67 degrees Rankine. And if we, and I'll do the conversions later, I'll just go up to a value up here. Okay, I'm just going to standardize it. Actually, let me just do this here again quickly. Yeah, so the boiling point of water is 212 degrees Fahrenheit. Brain farted for a second there, just calculate it out, and I am going to show you that. So if we were going to figure out what the boiling point of water was in Rankine, we see that we have a value of 459.67. So we would take that value and add it to 212, so plus 459.67. And we get a value of 671.67. So 671.67 degrees Rankine. So those are values to know. So know that 0 degrees Celsius is the same as 273.15 degrees Kelvin, and that would be the difference. If I have a value in degrees Celsius, I would add 273.15 to it to get a value in Kelvin. And if I have a value in Fahrenheit, I would add 459.67 to that value to get a value in Rankine. All right. So, conversions, how to do them. So let's do, we want to do Celsius to Fahrenheit. And from the little table that I showed you, Fahrenheit is typically always going to be a larger number than degrees Celsius. So when you get down, I believe it's negative 40 degrees Fahrenheit, is also negative 40 degrees Celsius, so that's the point when they are the same. You will find that the value is larger. So you're going from one value and it's getting greater. So Celsius to Fahrenheit, your answer should be a larger number. So if I want to find out what degrees Fahrenheit is from Celsius, my formula for that, so the number has to be bigger. So there's a multiplier of 9/5 times my degrees Celsius plus 32. So 9/5, we're going to use that. So that works out to, I think, about 1.8 as a value if I did 9 divided by 5. But you'll see why I'm leaving it as a fraction, because when we end up going between the two, we're going to have that 9 and 5, but we end up taking the reciprocal, or the upside down value, the reverse of it, when we're going in the opposite direction. So 9/5 times degrees Celsius is going to give you a larger number. And then we add 32 onto the end of that, and that is a constant. When we're going the other direction, and we have degrees Celsius, we are going to do things the other way. So we take our degrees Fahrenheit, and we want to do things in the reverse that we did when we were going forward, or when we were going to Fahrenheit. So the last thing we did was to add 32 onto the end of it. Now we want to do the reverse of that. So we take our degrees Fahrenheit and we subtract 32 from that value. And then in Fahrenheit, or when we're going to Fahrenheit, we multiplied then by 9 over 5. Now at the end of it, we multiplied by 5 over 9. So we took the reciprocal of 9 over 5, and that is a decimal, I think, is about 0.55. But that's what you need to do when you want to bounce between the two of those values. So not overly difficult, it's just you need to do things in the right operation. So when you're converting to Fahrenheit, you do that multiplication, then you add 32, and when you're going back to degrees Celsius, you subtract the 32 first, then multiply by 5 over 9. So let's give an example of that. We'll leave those two formulas there, just as a reference. Let's say I had a value and it was 20 degrees Celsius. 20 degrees Celsius, and I want to convert that to degrees Fahrenheit. So the formula I would use would be this top one. I'm trying to find degrees Fahrenheit. So I plug that into my formula. So degrees Fahrenheit is equal to 9 over 5 times 20 plus 32. If I plug that into my calculator, we get 20 times 9 over 5 is 36, and then we add 32 to that, and we get a value of 68. Let's put that over here. That's equal to 68 degrees Fahrenheit. So 20 degrees Celsius is equal to 68 degrees Fahrenheit. Now, if I was to go the other way around, now we're going to have a value in degrees Fahrenheit. Let's do 95 degrees Fahrenheit, and we want to go to degrees Celsius. Now we're going to go the opposite direction. So we have we're trying to find degrees Celsius, and we would put in 95 degrees Fahrenheit, and we want to subtract 32 from that, and then multiply it by 5 over 9. So we take 95 and subtract 32, which gives us the value of 63, and then we are going to multiply that by 5 over 9, and we get a value of 35, that was a terrible 5, 35 degrees Celsius. Okay, so fairly straightforward. Sometimes takes a little bit to get used to, but it's not all that bad. Okay, so now I'm going to just add that little conversion. Actually, I'll put some values up on the board, and I would like you, before I go through them, to just try them on your own. Pause the video if you want, and then work your way through them, and then I'll go through those values as well. Let's erase those. So I'm going to give you a bunch of values. The first one, so the one I mentioned, which can be a little trippy when you see it. Let's do negative 40 degrees Celsius to degrees Fahrenheit. 79 degrees Fahrenheit to Celsius. 132 degrees Celsius to Fahrenheit, and then negative, let's do negative 161 degrees Fahrenheit to Celsius. So pause the video, work through those, and what I'm going to do is I'm going to just end up pounding them out on the side. I won't do putting them into the equation, but I will give you all the answers for those, okay? So for the first one, I said they are the same value, so negative 40 degrees Celsius should be negative 40 degrees Fahrenheit. So I'm going to put that in. So we're going to do, with our formula, we are going to do, we're getting a larger number, so we take our negative 40 and we multiply it by 9/5. So you get a value of negative 72, and then we add 32 to that, and we get negative 40 degrees Fahrenheit. So just like what I was saying. So that is a crazy thing to see, and if you look at one of the old mercury thermometers, you know, the one with the bulb at the bottom, with the red mercury inside that goes up and down, you will see that negative 40 degrees Celsius and negative 40 degrees Fahrenheit are the same value. So let's look at 79 degrees Fahrenheit now. So we have 79, and now we're going the opposite way. So we subtract 32, and we multiply it by 5/9. And remember, we're going for a smaller value, and we get a value of 26.11. 26.11 degrees, and it is repeating degrees Celsius. Now 132 degrees Celsius, 2 degrees Fahrenheit, 132, and we're going to a smaller number, so, or sorry, a larger number, so we multiply by 9/5, then add 32, and we get an answer of 269.6. So 269.6 degrees Fahrenheit. And for the last one here, we have 161 degrees Fahrenheit, and we're going to a smaller number, so we do negative 161. So we're going to subtract 32 first, which gives you negative 193, and then multiply it by 5/9, and we get a value of negative 107.22 degrees Celsius. So hopefully you got all those, and those are fairly straightforward. I am going to try and add some questions online for you under the content section, and then I do have that pre-test that will be available for you as well. Now we're going to go the other way and look at Kelvin and Rankine just quickly. So if I wanted to, remember we had our values of 273.15 and 459.67. So that was for Kelvin, and this one was for Rankine. And I won't ask you anything overly crazy, but if I ask you a value in, let's say, Fahrenheit, and I want to know what that is in Kelvin, those will end up being two-step processes where I have to transfer from Fahrenheit to degrees Celsius, and then from degrees Celsius to Rankine, or sorry, to Kelvin. And then if I gave you a value in Celsius, I wanted to figure it out in Rankine, you'd have to go from Celsius to Fahrenheit, and then Fahrenheit to Rankine after that. So let's just combine them all together since you know how to convert. So let's go with, we'll do just a couple examples of this. Let's do 10 degrees Celsius to Rankine. So we know already that in order to convert from one to the other, so we want to go to Rankine, and Rankine is linked with Fahrenheit, so we take our 10 degrees Celsius and we change it to Fahrenheit, so we end up getting a value of, and we're getting a larger number, so 9/5 times 10 plus 32, and calculator, we get 10 times 9/5 gives you a value of 18, plus 32 gives you a value of 50. So that gives you a value of 50 degrees Fahrenheit. And then now I want to add 459.67 to that in order to make it a value in Rankine. So if I add 459.67, I get a value of 509.67 degrees Rankine from that. So 10 degrees Celsius is equal to 509.67 degrees Rankine. There are some other conversion formulas you can use to go directly to it that I have seen that are out there, or between Kelvin and Rankine, but I think on a whole, if you end up, or if I end up giving you way too many formulas, it's going to end up being a little more confusing. So if you stay with these values, know those values, and know how to convert between Celsius and Fahrenheit, it'll make your life quite a bit easier. Okay? And we're going to do one example going the other way. So we have a value of 72 degrees Fahrenheit to Kelvin. Okay? So to convert to Celsius, we know that the number needs to be getting smaller. So degrees Celsius, and our formula is our 72 degrees Fahrenheit, subtract 32 degrees Fahrenheit, and then we multiply that by 5/9, and that value makes it a smaller, give a smaller value because it works out to be a decimal. So we get 72, subtract 32, gives you a value of 40, and multiply that by 5/9, and we get a value of 22.22 repeating. So this is equal to 22.22 repeating degrees Celsius. And then all we need to do is to add our 273.15 to that, and we get a value in Kelvin, so plus 273.15, so that gives us 295.37. 295.37 degrees Kelvin. So not too bad to go between those. So as I said, yeah, I'll put some conversions and I'll have everything in there for you to try out, and then I'll take them up at a later date. Next thing I want to talk about, and this will be in that video, I just want to introduce it a little bit. It doesn't fully talk about thermocouples, so I'd like to talk about thermocouples, the RTDs, and the thermistors just a little bit. Thermocouples end up using two dissimilar metals. So those two dissimilar metals end up being taken, and they can be either twisted together or they can be soldered together. Let's just draw it as if they were twisted together. And So this could be, I don't know, this could be copper, and possibly this one iron. And those two values, or those two metals, when they're twisted together, end up, once a flame, we'll do a little candle, once a flame heats up that hot junction, or the junction that's going to be in the flame, it ends up producing a voltage. That voltage that's produced is based on the fact that there ends up being a flow of electrons in the copper wire that ends up flowing at a different rate than in iron. If they were both the same metals, and if I put a voltmeter over here, and it would be a millivolt meter over here, if they were the same values, or the same types of metals, so let's say I had copper, and copper, like you would have in a typical circuit, actually that may not be, maybe nickel, let's do nickel for that. We would end up finding, but if they're the same metals, both copper, electrons would flow at the same rate, so I wouldn't end up getting any potential difference between them. But if I use two dissimilar metals and heat those up, the rate at which electrons are going to flow, so obviously if I heat up wire, it's going to create energy, so those valence electrons are going to move from one side to the other and produce a potential difference across the wire. The same thing will happen in the nickel, where I have a potential difference from one side to the other, but it happens at a different rate than it does in copper. And that voltmeter is going to look at what the potential difference is between those two metals. And we end up finding that there is a small millivolt difference between the wires when we end up heating those up. So now we've generated a voltage simply by adding a flame to this. Now obviously that's a very small voltage, but what we can do is add multiple ones of these together. And even in Dalmars does also talk about this, and we heat them up and we put them in series with each other. This is going to then increase or add the voltages together if we do them in series. So we do those in series, we connect a voltmeter, millivolt meter to both of those, and the more that we put in series with each other, or we pile together, the greater the voltage is going to be. The term for multiple thermocouples that are added together or piled together, the reason why I say pile is because they're called a thermal pile when you have multiple thermocouples added together. So if I wanted a greater voltage output or a greater potential difference from one side to the other, I would end up using a thermal pile. And as I've said to some of the classes already, that this type of instrument ends up being used primarily in heating situations when I want to control a gas valve. So this thermal pile, so let's say I have both of them together, they would end up coming over to a solenoid that's in a gas valve, and there would be a little plunger. Let's say that this is the flow for gas through from one side to the other. I'll just draw one of the valves here. And when I produce a flame, I create an electromagnet that pulls that plunger down so the gas can flow through. But when the flame ends up turning off, that de-energizes that solenoid, and this valve is obviously a piece of metal, and it ends up popping back up. And restricting the flow of gas through that gas valve. These are used a lot for like a safety feature in gas appliances. So if there's no flame present, I won't be able to start up my gas appliance. Or let's say I have a flame and my gas valve is open and everything's working properly, and then possibly there's a issue, maybe I have a downdraft, or I start getting a lot of soot inside or being produced, or that thermocouple or thermopile gets covered in soot. It will then decrease the voltage output from the thermocouple, and when that thermocouple voltage is reduced, then obviously my solenoid won't have enough current there, or potential difference in order to keep that solenoid energized, so my valve will then close. Typically a thermocouple, when I see it, or a thermal pile will typically be in an enclosure. So the wires of my thermocouple will go up inside, and those two dissimilar metals will be up inside here. And what they're doing is waiting for that flame. So if I have a pilot assembly here, that was terrible at the end there, pilot assembly, the gas is going to be coming up and producing a flame, and that flame is going to come out both sides of this pilot assembly, but the flame will heat up that little thermal well that the thermocouple's in. And a thermal well is just a protective place for that sensing device to go into. So thermocouples or RTDs typically will be found in a thermal well, and it prevents it from obviously melting the casing or whatever else. But it needs to see that flame all the time. However, when you put something into a flame or impinge on a flame, what can happen is I produce soot buildup on the outside of this thermocouple. And if you end up having maybe hot water here that doesn't work, or you have a furnace that stops working, one of the biggest things is that I end up getting soot buildup. And when soot buildup is on the outside of that, so soot buildup is carbon buildup, the heat can't get into or be sensed by that thermocouple as well as it would have if it's just pure metal conducting that heat in. So what you end up having to do with them is to go in and clean that soot off of that thermocouple. And one of the best ways to do it is with a little bit of sandcloth or sandpaper, or sometimes even steel wool. Restaurants will have this happen a lot with their deep fryers. I've been in to do stuff like that, and something that's on hand, because you don't always have sandcloth on you unless you're a plumber. So what I've done is I'll go and get a new little like scrub brush, like steel wool, and go over and I will clean off the soot with the steel wool, and then it allows the heat to conduct through to that thermocouple again, and produce a voltage to keep that gas valve open and running. There's 4 main types that I want you guys to look at. There's type J, type K, type T and type E. And with all these, you're going to find, and I will have a little handout for you in your next lab class. And in the video, you will see a little bit where it talks about it. But they typically have, or not typically, they always have two different colored wires. In all the cases, one of them is red. So type J, type K, type T, and type E all have a red wire. And if you just looked at it on the outset, oh, all these have a red wire, that must be my positive in a thermocouple when I'm looking at the two wires. But in actuality, the red wire in a thermocouple is my negative, not my positive. And I'm pretty sure there is a test question that's based on that. So when you see red, red is always going to be my negative, 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 and negative. The other wire, so when I type J, the other wire is white. And I like to try and think up some form of acronym for knowing what color is what, just so you don't always have to look it up every time. So white, J, W, you could use Jack White as a way to remember. So one of those wires is white, J-E-W, Jack White. And now let's do K. K has yellow. Okay, and I'll just put all these in first. Type T is blue, and type E is purple. So type E, I think EP, eggplant. Eggplant is purple. TB could be Toronto Blue Jays, right? For it to be blue. And for K and Y, you could think of anything that you want. There is a certain thing called KY. I won't get into what that is, but you can come up. I don't know if you noticed, I did avoid that one a little bit. Let's see if we can think of a good one for that. Let's do I can't even think of anything other than that. You might be able to come up with something. Maybe I've had that as my value for so long, or my thing for so long, I can't think of anything else. But yeah, KY is yellow. So yeah, so no, type J is white and red, type K is yellow and red, type T is blue and red, and type E is purple and red. If you end up looking up a table for these values, you'll see that all of them have, and in lab class I will show you, all of them do have a different temperature range that they can be used at. Type K is the most common thermocouple, and you'll see it in lab class. So it's the most common, it is the cheapest, and you will find there are more thermocouples than this. These are the most common, but type K is used over all of them, and that's because it also works on the highest temperature range. I believe it's works all the way down to minus 300 degrees Celsius and all the way up to plus 2,250 degrees Celsius, I believe. So huge temperature range, and in that entire temperature range there is a greater voltage that's produced. So as temperature goes up, the voltage output is going to be increased. So you could even do that with your fingers or with a lighter, but all are acceptable. And you'll find with a lot of testing equipment, so for thermocouples or RTDs or thermistors that cost can be a big determining factor as to what you end up using in a certain application. And then also the the specific type of application can change or be what's most suited. So I get a voltage output, and a voltage output can be transmitted over a long distance. So maybe I want to have it as a voltage output anyways. So if I keep it as a voltage output anyways, I would want a thermocouple. If I want to use an RTD, and also, sorry, let me also mention the robustness, or how strong the device is, can also be a determining factor. So thermocouples, typically in their enclosures, are fairly strong. An RTD is fairly strong. They normally get put in a thermal well. So a thermal well, and I'll show you a big one in class. Thermal well has a little top cap on it, and then the sensor ends up getting put in that well to protect it. They're fairly robust. But what you end up finding with thermistors, a thermistor, and I'll go through the RTD and the thermistor. The thermistor is just a semiconductor, and it almost looks like a small little capacitor, and that only has two thin little wires on it, and that semiconductor material ends up changing its resistance based on the temperature, but they are very flimsy and can break fairly easily. So if you're in an area where there's the chance of something being damaged, this is not one of them, your thermistor. But thermocouples are good, so all based on application, and RTDs. Okay, so RTD is the next one I want to talk about quick. RTD, and that is a resistive temperature detector, and a RTD, they can be found in, they can have either 2 wires, 3 wires, or 4 wires, and the number of wires that come with them are, the more wires are just to kind of allow for, if you go over long distances, there can be error, because obviously if I have a sensing device, so let's talk about the most common one, is a PT100, and a PT100 at 100 degrees has a resistive value, or sorry, at 0 degrees has a resistive value of 100 ohms. If I connect that to wire and go to travel over a long distance, that wire in itself is going to have a resistance to it. So if I'm on the other end and I go to put, and I have a piece of sensing equipment or a meter that's registering what that resistance is, and I see that it is maybe 104 degrees, or maybe, it could even be that there's heat along the way, heating up part of the wire, which can also increase the resistance of the wire. I'm not going to get a true accurate value on the other side. So if I add multiple wires, and those wires are just going to be in parallel with the other ones. So if I have my little RTD, which typically is platinum wire, and then on a little ceramic grid, and this is the positive and this is the negative, that would be a 2-wire one. A 3-wire one would have an extra one coming off, and it reduces your error that might be in the wire, because now I have two different wires that are going to be end up seeing what that resistance is, not just one. And if I have a 4-wire one, it's going to be coming off of the negative. So there's not a huge difference, it's just there's multiple wires on the positive, multiple wires on the negative. And you wouldn't necessarily see a 4-wire unless you're in a lab circumstance. Typically a 2 or 3-wire RTD is what you'd end up using. So, what you do find is typically most wires. So if I have a chunk of wire, let's say it's copper, and I put a flame on it, what it ends up doing is, as heat is put on the wire, it will end up increasing the resistance of that wire. So that's for copper. So as heat goes up, resistance goes up, and then as heat goes down, obviously vice versa, the resistance will go down, and that is referred to as positive temperature coefficient. So PT, positive temperature. So positive temperature coefficient. And all that means is that as temperature goes up, resistance also goes up. If temperature goes down, resistance also goes down. So rather than copper being used, platinum ends up having a fairly wide-ranging resistance, or fairly large resistance change based on temperature, but it is an even change. So per degree Celsius, the resistance error is from, like, I think it's 0.1 per degree Celsius, so it's quite accurate, and it's a linear relationship. And that platinum wire on that RTD, as I said, typically is brought out on a little pattern like that and put on a slab of ceramic, or encased in a slab of ceramic, and then that whole thing is covered in glass to protect the whole thing. And then the other option, the other thing that you sometimes will see, is there ends up being a ceramic tube, and the wire, platinum wire, is wrapped around the ceramic core, and that is covered in glass. And that literally would just get put in a room, and could be matched with a thermostat. So at 0 degrees, it's going to read 100 ohms, and as the temperature goes up, because it's a positive temperature coefficient, the resistance at the same time is also going to go up. So what you'd end up doing with it, and you could see with it, and what they would originally did, is they saw what the resistance was at 100, or let's say 0 degrees, and looked at what it was at 100 degrees Celsius, and found and calibrated all the equipment based on that, so the sensing devices or thermostats based on that, and found that it went up evenly in between. So let's say, I don't know, at 100 degrees Celsius, let's say it's 120 ohms. Then halfway in between, if I looked at 50 degrees Celsius, then I would have a resistance of 110 ohms. So I could be in a completely different room, look at the resistance, or my sensing equipment can look at what the resistance is and tell exactly what the temperature is at the time. So if it's heating season, it can allow, if it's too cold in the room, it can allow the heater to come on, kick on, heat it up. And if it's too cool in the room at that time, if it's too hot in the room and it's air conditioning season, it can see that, oh, it's too hot, the air conditioner needs to come on, and it does change its resistance basically instantaneously with a temperature change. So excuse me, it is an extremely good option to use. The last one I'm going to look at in this video is a thermistor. So therm, basically thermometer and resistor combined. It is a piece of semiconductor material, and so I'm sure in Ed's class in theory, he would have went through semiconductors. So semiconductors have, I think it's, I believe, 3 or 4 valence electrons in them. But with that semiconductor material for that thermistor, they end up also having a resistance change based on a change in temperature. So as I said, they are typically just a chunk of material, semiconductor material. I can't think off the top of my head which materials. Probably silicon would be the semiconductor material that would be used for them, and its resistance changes based on temperature and a set amount, just like the other one was. The majority of these, though, are negative temperature coefficient. So negative temperature coefficient. There are some positive temperature coefficient ones, but the majority of them are negative temperature coefficient. So if I were to look at a graph, and if I were to look at temperature down here, resistance over here, as the temperature goes up, so this is low, high, as temperature gets higher, my resistance is going to go down. So that is negative temperature coefficient. There are some positive temperature coefficient ones. So this is NTC, negative temperature coefficient. A positive temperature coefficient, as the temperature got higher, you would end up seeing it go in the opposite direction. So that is PTC, positive temperature coefficient. So majority of them are NTCs, and the RTDs are typically positive temperature coefficient. Just know the difference between those two. And these are used a lot with the smart thermostats. So like the Nest thermostat or the Lyric thermostat, and Honeywell has a lot of really nice little, if I can remember, I'll bring one in next week. The little sensor, Honeywell sensor, it can go up in a room. So typically at maybe restaurants or apartment buildings, if you don't want the client or the customer to be able to change the temperature, you just put a little thermistor in the room, and then it sends the signal back to the thermostat saying what the temperature is, so no one can screw with it. But the only thing, as I said, is it is very weak. They are in an enclosure, but if that ends up being taken apart and ripped apart, obviously it won't work. So typically in a setting where there isn't a lot of chance for damage, I would put those in. But the nice thing with them that I've seen is sometimes you've got a very old system in a house, and let's say you just had a heating system and you wanted to add in heating and cooling, and maybe your thermostat wire that goes upstairs only has 2 wires or maybe 3 wires, and with the new thermostats you need a heating, a cooling, a common, which the other ones don't have, and then I would have a fan wire, and also my power wire. So a lot of times you need 5, possibly 6, sometimes even 7 wires. So rather than having to run new wire through your house to accommodate the new thermostat, the thermostat can just stay right by the furnace, and I run a little remote sensor, a thermistor to upstairs, and it only needs 2 wires because there's only 2 terminals on them, and so I can do the exact same thing without having to add all that extra work into that. So I don't really think I need to do too much more. What I'm going to do in the next class is introduce an RTD or a thermocouple into a Wheatstone bridge, which I know you guys absolutely love. And when we were talking in the last class about that transducer with the pressure lab, and how there's that pressure sensitive resistor that was in that Wheatstone bridge, and then I got a different value output across A and B on my Wheatstone bridge. Now with this, I can put in a thermistor or an RTD, and based on temperature change, my resistance can go up and down. So I can incorporate those types of questions into this conversation on temperature, and also, to my delight, not yours, add them onto the test. Okay? So that's everything for this video. Please watch the other video that I am going to have linked in the announcements as well, and it'll visually show you a little more of what I was talking about. Okay? Have a good day.